Hi, my name is Madeline Lee,
And I'm Luis Benitez.
and we are HRS Bottom Geometry. And so I'll start off with our introduction. And the problem that we've been experiencing is flock buildup, which occurs during sedimentation at the bottom of our tube settler, and it's really time consuming to clean. So the importance of avoiding this flock buildup is that reducing cleaning time allows researchers to spend less time cleaning the apparatus and more time running experiments. And this is something that's present in the Agua Clara lab only and not in our plants, but it's good to figure out this problem in our lab. And the current hypotheses that we're running our experiments off of is that the bottom geometry of a sedimentation tank influences the flock buildup, and flat bottoms allow flocks to stack on top of each other, contributing to buildup. And this is an image of the coupling that is in the bottom of our apparatus. And we've also determined that cone shapes contribute to buildup. And our goals for this semester are to develop an insert that modifies the bottom geometry to prevent such buildup. So here is an image of one of the geometries that we will be testing this semester. And Luis will talk more about our previous work.
Okay, during the summer of 2018, that sub-team discovered that flat bottoms don't work because they lead to gelling, and that regular cone shapes don't work as well, as can be seen by that diagram, because it allows the flocks to stack up in rings instead of just onto each other again, but that's still a problem. But what they did discover was that slanted slopes are a good design because they allow the flocks to resuspend and the gelling to occur less frequently. And the flock resuspension can be seen in this video. Yeah.
And I'll talk more about our methods. So here is an image of our apparatus. It consists of 4 pumps, 2 stock tanks, one for clay and one for coagulant, and 2 turbidimeters, and our tube settler, which is where sedimentation occurs, and it's also where we experience flock buildup. And we use Python calculations to figure out the RPM for the water and the coagulant pump, and we use Procoda and PID control to control the clay pump to ensure that the influent turbidity is 100 NTU. And here is an image of our stack cylinder. It's one of the inserts that we designed this semester, and the top portion reflects the same geometry that we had in a previous image. And here's an image of our linear cylinder, and the difference is the angle and also the shape. And and I'll talk more about our results and analysis. So here is an image of our baseline experiment. The parameters include that it ran at using the old tube settler and also at a 2 millimeter per second upflow velocity. We also didn't use an insert for this experiment, and as you can see in this figure, gelling was observed. So here is a graph of our results, and you can see that there's an exponential increase in turbidity depicted with this orange regression line. And because the coupling had a flat bottom, flocks were able to stack on top of each other and produce the buildup that was seen in the previous slide. And this is the results from our stack cylinder. And the slope angle of the stack cylinder was 41 degrees. And this experiment was run with using the old tube settler and at a 2 millimeter per second upflow velocity. And as you can see in this image, that gelling was observed. So here is the graph of our experiment, and you can also see again that there is an exponential increase in turbidity depicted by this orange regression line, and gelling still occurred. So we had to take into account rolling friction and the equation Q equals AV in our analysis. So starting with rolling friction, initial rolling friction did not affect the flocks as much due to their individual weight, but as the flocks began to stick to each other more, rolling friction began to affect them more as they began to stick to each other and increase more in weight, and they started to slide down the slope more slowly, and because of that, flocks had the opportunity to stack on top of each other and increase their weight, which would also increase the stacking and the amount of buildup that was produced. We also took into account Q equals AV. So Q equals AV represents flow rate equals area times velocity. So our flow rate was held constant, but the area began to decrease due to flock buildup. So velocity V had to increase to compensate for the decrease in area. And because the velocity was continually increasing, flocks could not recirculate and resuspend and therefore began to stack more on top of each other.
Okay, so due to an incident in a lab, we had to change tube settlers, but the new tube settler was very similar to the old tube settler except for a test tube attachment, but that did not affect our experiments. So we ran another baseline experiment with the new tube settler still at 2 millimeters per second, and we obtained similar results, and because it can be seen in the picture, gelling still occurred. And these are our results. The figure on the left represents the old test tube results, while the figure on the right represents the new tube settler results. And as can be seen, the effluent turbidity was still around the same range, and there was still an exponential increase in effluent turbidity, which again meant an exponential decay of our flock blanket. So once we ran our linear cylinder experiments, with the new tube settler, we obtained this result, as can be seen from the picture. There was a lack of gelling, and from the results that we obtained, there was a low effluent turbidity, and there was also a linear increase in the effluent turbidity, which corresponds to a linear decay of the flock blanket, which is what we want in our experiments. And this meant that we were getting positive results. We ran another baseline experiment, but this time at 3 millimeters per second. As can be seen in the picture, there was no gelling once again. And with the results we obtained, yes, the effluent turbidity was high, but it still decay. There was still a linear increase, not exponential. So this is what we want, and so we deemed it unnecessary to run an experiment with the bottom geometry. And we have concluded that a 41-degree angle doesn't work because it still allows for gelling to occur, whereas a 58-degree angle is very beneficial because it leads to no gelling, which is what we want. And for future experiments, we will be testing with an upflow velocity of 1 millimeter per second to see if flocks are still able to reducing flock resuspension, and see if our bottom geometry of a 58-degree angle still works. We're also going to be working with longer tube inserts because we want to see how the bottom geometry interacts with the flocks. Thank you for listening.